So we start by taking a look at some of the questions regarding the span. Let's remind ourselves what span was. Span is set of, so this is span of a set of vectors. Just for concreteness, call them U, say V, W, and you could have some other stuff. That is set of all linear combinations. That can be constructed from these vectors. Well, what is that? Is a set of as many U's as you want to take, let's say AU, as many V's you want to take, as many W's you want to take, and just add them all together. And if you have more vectors, just keep doing this thing. Do this for all possible values of these numbers. A, B, C are real numbers. What can you make from them? We said for the case of two vectors, it was not so unusual. So if I have two vectors, suppose I have this green vector and this red vector. If I consider all linear combinations of these two, what do I get? Very good. We get the plane on which these two vectors could be seated. Because I can arrive at any location in this plane by taking an appropriate multiple of the green, an appropriate multiple of the red one, and that brings me to that spot. We said there are certain pathological situations, like if your vectors aren't really independent vectors, like if I have such a red, green, and red vector being, say, half as big as the green one. The set of all linear combination of these two is going to be what? It's just going to be straight line. We are not going to, these guys cannot help each other to get off of that line. So we are just stuck on that. That's going to be the span of those two. The span of these two is this plane. If you have three vectors, so if I have this vector, some other vector, and a third vector sticking out of the plane on which the first two are sitting, what do you think the span of them going to be? If I have three vectors, such as these two pens that I got hold in my hand, and say this one. So I have these three vectors. What would be their span? Every point in this room, every point in the entire space actually can be reached by taking appropriate number of steps in the green direction and the red direction and say this black direction. That's going to take you to wherever you want to go in space. So if these three vectors are situated in such a way that not a single one of them is seated on the plane of the other two, it is truly independently, it is sticking out of the region defined by the other two, then the space that you can arrive at by combining these is the entire three-dimensional space you can imagine. Any point in that space can be arrived at by combining these. We are going to come back to this issue in a lot more systematic way later on. Right now we are just making our feet wet, really, and not we're not looking at it in a very deterministic fashion. So let's go to, say, problem you were asking, 21. 21 has several components. The first of them is asking what is the span of 0, 2, 2, 0, minus 1, 1, 0, 0, 0. Well, these are vectors in 3 dimensions, and I hope you have seen some three-dimensional math in some of your classes. You're supposed to have taken Calculus 2. At the end of Calculus 2, you see a little bit of that, and hopefully you have seen it other places. So it's not going to come as a major surprise to you that we could have a 3-dimensional coordinate system. So here's my x, y, z. This we are going to refer to as x coordinate, y coordinate, z coordinate. So 2 and 2 are in the y and z axis. So 2 and 2. So this is the point, and this is going to be the vector that corresponds to 0, 2, and 2. So I have no x's, y2, z2. The other one, let's say this is 0, minus 1, and 1. So my y is minus 1. I'm going back. My z is 1. So I am visualizing things in 3 dimension is a bit tricky, but here's your chance to practice. 0, 0, 0. We are not going that far with that one. So that is our 3rd vector. Question is, if I take all linear combinations of these 3 vectors, the green and the blue and this black one, what portion of space can I reach? Okay, very good. This back plane here, any spot on it can be arrived at, but I cannot get this is the YZ plane, but I can't stick my head out of that. That is, I can't travel in the x direction because none of these vectors let me travel in the x direction. They don't have any component coming this way. They have components in y and z, and these 2 vectors, just visually checking that they are independent. One of them is not a multiple of the other one. They are not lined up. So this back plane can be arrived at. So this is, first of all, it's a plane. So like, that's the half credit to say it, to recognize it is a plane as opposed to say a line or an entire space or just the origin itself. Icing on the cake, next stage or the next 50% of this, or what plane? Can you describe anything about it? So this is the y, z plane of the 3-dimensional space. So that's the answer to part A. Any question on this before we go to part B? Is that clear what we're doing? Part B. Yeah, it's we need to nail it down in a problem such as this where it is kind of clear. It's not something that's going to escape us. But some other problems in the future, it might be trickier. You know, some nondescript plane in space has no name, so we don't say what it is. But if it has a name, we have to nail it down. Part B says do the same thing for the span of 1, 0, 2, 2, 0, minus 1, 3, 0, 1. Okay, before we draw them, what aspect of these 3 vectors strike us? Like, is there anything peculiar about them? Yeah, none of them have any y, so we can't stick our head out in the y direction. So at most, what is it going to be? At most, it's going to be just the xz plane, or perhaps some subset of that one. So we noticed quickly that there's no y component. So whatever the answer is going to be limited to xz plane. There are only few choices left there. Whatever it is, it has to be inside of this left plane here. Well, let's check it out. 102 is 102. We are going 1 to the right, nothing to the, excuse me, 1 forward, nothing to the right, 2 units up. So at this point, we remember to draw the lines parallel to the axis, not straight but parallel. So this is going to be our first vector. Then other one, 2 0 minus 1. So this one I am taking 2 steps in the x direction, minus 1 step in the z direction. So if you this is 2 0 minus 1. The green and blue already have a span that is equal to what? That's just the xz plane, and we couldn't have anything more than xz plane anyway. So we could already say that the span is the entire xz plane. Span is xz plane. So what is this guy doing? It's kind of a redundant component. It kind of adds to the force that we have, that this is 301. It's 3 steps to the right, 1 step up, indeed any 2 of them would have created the same span. Any one of the 3 could be considered as redundant and not contributing to the span. Like if you wanted to be economical, you could have relied on any 2 and it would have been fine. This 301, we're going to say it is a linear combination of the other 2. Like what combination of A and B would create C? Just simply adding them. C is equal to A plus B. So anything that contains A, B, C could also be written in terms of just A and B. You simply replace your C's by A plus B's. So this is redundant, is the sum of the other one. If you wish, you could think of B, or the blue one, as redundant and write everything in terms of A and C. If you wish, you could think of A as redundant and write everything in terms of B and C. So a span of this one is the XZ plane. And so you continue with the part C and D. Let me just ask quickly, how would the answer be different with respect to, say, D? Anything strikes you about these? So let me just quickly wrap this up. So the question is, what is the span of, let's say, 1, 1, 1? This has, the other one is like this too, but let me just write this one. 5, 5, 5. Yeah, so if you say A, B, C, there's something strange about these vectors, kind of speaks loud, that B is not really independent from A, just copy of it, stretch the other way. C is 5 times A. So if these guys are already written in terms of A, they cannot contribute to any new dimensionality for us. So the span you said is what? Just a line. Like if I consider A, one space in each direction, so 1 to the right, 1 out to the right, 1 up, so say this is A. B is just in the same extension of A, and C, again, no news here, C is also 5A. So linear combination of these, whatever you do, span is a line that is smack between the 3 coordinate systems, 3 coordinate axes, same distance from all 3 of them. if you have taken calculus 2, end of calculus 2, beginning of calculus 3, you have a description for that line. So the description of a line is that on that line z and y and x are all the same. That's a description of this line. So what line is it? It's that line. But it's not a coordinate line or anything like that. Doesn't have a name. Okay, so that is part D. And then you do the other one yourself. Let's move on to the issue of the Gram-Schmidt process. Okay. So what's the issue here? The issue is in life we like lines to be perpendicular to each other. This situation is a lot easier for us to handle than two vectors that perhaps make some kind of arbitrary angle between the two of them. The question is, if you are dealing with some kind of a engineering situation or physical situation where your vectors are like this, can you create another set that is related to this set in the sense that we are going to describe, but their angles are turned into 90 degrees, kind of forcing a system to be opened up, like you have such a thing in a certain manner, a certain constrained manner. We want to open them up so that the angle becomes 90 degrees. Of course, with respect to 2, it's not a big issue. The topic comes up in any number of dimensions, and really its application is when you have many vectors in high dimensions and you want to kind of force them to bloom up and open up, as opposed to just a situation like this where you could have 3 vectors making arbitrary angles between themselves, as opposed to having like a corner where all the angles are 90 degrees. So Gram-Schmidt process is a way of opening things up. There are plenty of choices you have there, and we have to kind of constrain it. Like if I got 2 vectors here and say open this thing up, and you say, okay, don't use these, use these 2 over here. So well, I want to open these guys up. I don't want to go somewhere else and do something altogether new. So the process that we have, we are going to call these things by some vectors. For example, we're going to call them V1 and V2, or say V1 and V2 and V3. And after we open them up, we are going to perhaps call them in a certain order, P1 and a P2, or say P1 and or let's say this is P1 and P2, P3, or some style. So we're using P's to indicate the result of our process where things are perpendicular. So P's are going to be perpendicular, and the V's are the original, which could be at arbitrary angle. What's the trick that we want to apply? Well, in a sense, we want span up whatever we are creating to match span up whatever we're having at the beginning. So we are not leaving the space and going to our backyard and doing something there. Rather, we want to be relevant to what we are starting with. So span of P1 has to be same as the span of V1. Span of P1 and P2 has to be same as the span of V1 and V2. Span of P1, P2, P3 has to be same as the span of V1, V2, V3. So both of them are describing the same space. It's just that one set is nicer looking than the other set. So here is requirements that we have in our mind. Span of P1 has to be same as span of V1. So we number our vectors in some way that are significant to us, and we get going after that. So how many vectors you got, step by step we are going to do our constructions so that the space that is described by these vectors, that is not changed. It's just that your building blocks are changed. The trick that we are going to apply is based on the idea of projections that we learned last time. Let me just quickly remind you what that one was. So we will use before I get down in the formulas, let me tell you what it is all about. Let me redraw the picture. So suppose I have this V1 and this V2. I want to force them open. That is, I want to create P1 and this guy will be P2. So okay, take V2, drop perpendicular and draw this one to this perpendicular line. Okay, this V2 can be resolved into two components. One is this one. One is this one. This is what we learned last time. We called it, what did we call that? This, the first blue one, let me let me call this vector T, or let me put it capital T. This one was projection of V2, so let's call T is equal to projection of V2 on V1. Like cast the shadow of V2 on V1. This is the shadow. Well, what should I do to V2? Utilizing this shadow, so that whatever is left is perpendicular to V1. I can think about V2 as two components, T and N. Is that right? V2 is the vector T plus the vector N. Now, what should I do to V2 so that N will be surviving member? So, yeah, exactly. Just take V2, shave off this shadow off of it. Whatever is left is just a normal component. And that normal component, that's what we are going to call P2. Okay? As simple as that. So, so we set, in some manner we get started with our first important vector. We're going to call it V1, and we just copy it through. We don't have to do anything there. P1 is just same as V1. P2 is, we say, take the next vector, V2. From that, subtract its shadow on the first vector. So we say projection of V1, projection of V2 on the very first one, which by now is just called P1. Okay, P2 is V2 minus projection of V2 on P1. I need a new page, so let me get started and do this thing again there. So let's just write the formula for this. So again, we have V1, V2, and then we open this up to P1, P2. Other question? Yes. So projection of V2 on P1. I'm going to write that again. Okay? Is that clear? Okay. So so we say P1 is same as V1. P2 is V2 minus projection of V2 on P1. So that is, now do you remember what was the formula for this? We learned last time V2 P1 over P1, P1, P1. Okay, looks a bit crowded, but that's first perhaps crowded formula we got. So here's our formula. P2 is V2 minus that thing. Remember, this is, whatever it is in direction of P1, and P1 itself is just a copy of V1. What is after this? We need to do two things. One is to practice this idea, and the other one is, what if I got a lot more vectors than just two? And that's where things become interesting. Most of the examples you have at most 3 vectors, but in applications these things are done on situations where there could be tens or hundreds of vectors. So let's just write that too, and then I come back to the practice. So suppose I have so the intimation here is that we have a 3-dimensional situation. So we actually have like X, Y, Z, and let me see if I can give the correct impression of what is it that we are. However you draw these things in 3 dimension, somebody misunderstands it. So let's see. Okay, we want to open them up and essentially recover our x, y, z axis out of our vectors. And so our first vector P1 is just copy of our V1. We don't have to do anything. To force V2 open, it's going to create our P2 for us. After we have opened this, we go after V3. V3, we cast its shadow on the existing vectors that we have created. Remove those shadows. Whatever is left is going to be our P3. So the formalism is going to go like this. P1 is just a copy of V1. P2 is whatever V2 was minus projection of V2 on P1. P3 is going to be V3 minus whatever shadow it casts on the existing perpendicular set that we already have. Whatever shadow it casts on V1, we remove it so it doesn't duplicate this direction. Whatever shadow it casts on P2, we remove that so it doesn't have any component going in that direction. So the only direction left for him to go is going to be straight up perpendicular to both. So that's going to be projection of the last guy minus, projection of last guy on the very first of these vectors we have created, and then projection of again that vector on second member that we have created. So on the right hand side, the subtractions that we do are the projections on the portion of the system we have already created, and then we go step by step, and if you had more, we just list more of these things. Now let me just go ahead and write the formula for this one too. So P1 is same as V1. P2, good practice for you to just rattle it off. What should I write here? Times P1. P3 minus what? P1, 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 and then what else? Minus? The most common mistake here is students take V2 here. take V2, it doesn't work. Your resulting vectors are not perpendicular. It has to be built up against the existing perpendicular vectors, not the original whatever you got. That has V2 has no significance anymore. It's just P2 that. So this is what we call Gram-Schmidt. This Gram-Schmidt process is a basis of certain ideas in calculations in engineering or numerical work. Before we go any further, let me say that it is not a stable process. So if you are going to become an engineer later on, you have to know ahead of time that there is a little bit of a fine print next to this thing. It's not really. So I don't want you to become a CEO of a Toyota and build a car on this and then come back and say, well, it's not working or something. So there is something about it that doesn't work in high dimension. The errors build up and things get out of whack. Things look nice in these formulas that we write, but when you want to do stuff, you operate in a world of limited resources. So these numbers are always done on a computer. Computers have limited precision. They don't have infinite precision to them. And so they just chop off numbers at some place. And an issue with any kind of mathematical formula is that if you have these chopped off numbers snowballing on top of each other, would things get out of hand? Would the final result be anything close to what you were expecting? And it's a tricky issue. One famous case of that is something that came up during the U.S.-Iraq war, that they had these Patriot missiles presumably hitting against Iraqi Scud missiles. So everybody was celebrating that these are actually hitting those missiles up in the air, and turned out none of them were hitting any missiles. On the other side, they were just exploding up in the air. Everybody was celebrating. But there was a problem with the finite precision of the timer on these equipments, just not keeping the time right, so things weren't just working right. So there is always an issue that the numbers that you work with are coming with error and have finite precision on your machines, and things that look nice on a piece of paper might not turn out to be that way on the actual situation. So let's just go ahead and take a look at one example. Since we are doing these things by hand and we are keeping all the numbers accurately as they are, there is no danger now. But there could be somewhere else. Well, we might as well take the very last of these. These examples are a little bit contrived, with all numbers having such a nice looks to them and such. But anyway, we have these three vectors. The question is, it's saying, so this is problem 50. Find perpendicular vectors P1, P2, P3 such that span of P1, P2, span of V1, V2, and the span of all three of them are the same. So it is telling us, okay, go ahead, make the other three vectors and watch out to stay within this prescription. Okay, that's what is requested in this problem. So who is P1? 1, 1, 1. Who is P2? It is V2 minus V2 P1, 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 P1. What is meant by this here? That's a dot product, is that right? So V2 R vector minus R vector 1 1 0, let me squeeze them here, times are divided by, I hope my handwriting is readable, times what? Yeah, 1 1 1. That's our P2. Let's just do that. So it's 1 1 0. Do the numerator for me. What is the numerator? Just 2. Denominator? Say it again. 3 times 1 1 1. So you have 1 1 0, 2/3, 2/3, 2/3. So what is that? 1/3, 1/3 minus 2/3. Is that right? That's our P2. So what we got out of this is that P2 now most engineers like to write 1/3 as 0.33, and that's the beginning of the trouble. So these numbers not being so nasty, we just keep them accurate as they are, as opposed to running for our calculator. So right now I just write it 1 1 minus 2. I factor the 3 out. That makes my life a little bit easier. Now I go for next round. P3. Who's P3? Say V3 minus copies of this type. P3, V3, P1, 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 and V3, P2, 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 P2. Now a word of advice: if you have found P1 and then P2, would double of P2 or triple of P2 just work as well? So that's right, is that? It's if this is perpendicular to the first one, you're making it a little bit longer or shorter, still perpendicular to the first one. So you might use that feature to make your life easier. Like if you try to use this, chances are quite high that over here you're going to make some arithmetic mistake. But what's a better vector to use, and actually resulting in the same thing? This would be better to use than a P2 itself. Why? First of all, a multiple of a vector is as good of a perpendicular to the other ones as the original one was. The shadows are not going to be any different. The advantage is that you don't have to live with the misery of dealing with all those fractional numbers, round off, etc. So that is actually preferred. So let's listen to that advice. Let's see if our life gets any better. P3 was 1 0 0 minus V3. So let's write 1 0 0 P1 P1 1 1 1 1 1 1 1 1 1 1 1 1. My handwriting becoming sloppy now, but this is not friendly environment to write. Minus V3 1 0 0. So instead of P2, what's a good thing to use? 1 negative 2. Notice if I multiply this by a number, that by a number, this one by a number, that one by that number, all of them are going to cancel each other out. So it's up to me. If I want to multiply all of them by 10, that's fine. If I want to multiply them by 100, that's all fine. Here, what makes sense to do is to multiply by 3. So that I just extract this number, P2, 1 1 minus 2, and that is going to be a huge lifesaver there. Okay, so you either use it like this and live with all the fraction stuff, or clean it out use this one. If you want to call that N2 or N3, that's fine. P3. Okay, help me out here. Numerator is 1. Denominator 3. Numerator of this one 1. Denominator say it again. 6. 1 times what? 1 times 1. Minus 2 times minus 2. That's going to be 1 times 1. Plus 1 times 1. Plus minus 2 times minus 2 makes 6. 6 of 1. 1 minus 2. So P3 is 1, 0, 0 minus, well, 1/3, 1/3, 1/3 minus 1/6, 1/6, if you wish, minus 2/6 of minus 2/3, minus, let me just write it, minus 2/6. So I take 1 minus 1/3 minus 6. Second component 0 minus 1/3 minus 6. Third component 0 minus 1/3 minus minus, and this is 1/3. So what is this one? This one minus 1/2, is that right? And this one 0. So P3 became 1/2 of 1 minus 1, 0. So let's write down our final answer. P1 was just copy of what we had, which was 1, 1, 1. P2 official algorithm starts with 1/3 of, but really 1, 1 minus 2 is just as good and actually nicer. P3 official algorithm ends up with 1/2 of, but really this one would be nicer. What do we do at this stage? We're doing a lot of arithmetic, so you might as well check. And that's where it breaks down in engineering algorithm. You go through this process, you use your calculator, you do stuff, you come at the end, you check, it doesn't check. And the reason is that the round off has built up so much that you're just producing quantities that don't make good sense. What is a check? Well, what is a check? You tell me, what is a check? That P1 dot P2 has to be 0. And again, the multiples don't count. What is really important is the ratio of the items inside. So what is the dot of these two? So P1, so that factor of 1/3, we are pulling it outside. P1, P3, that is, check that 1, 1, 1, dotted with 1 minus 1, 0. There's a factor of 1/2 in front of it, but that doesn't count either. When you multiply, what do you get? 0. And P2, P3, you have 1/3 and 1/2. Again, that they don't count. 1, 1 minus 2 dotted with 1 minus 1, 0. That's again 0. So you make sure that you check your stuff. Okay then. So you finish up the section on for Monday. I want you to hand me the following problems. So you do 48. There's not really enough problem here to assign, so but from 3-1. Okay, you hang on to that until I assign another problem and then collect it all on Wednesday. Okay, good luck and God bless.